Welcome back, guys. We've been getting a lot of feedback concerning the structure of the fiber and how it is that the atom is able to change shapes, how it is that filaments are able to transect one another, and perhaps most importantly, how it is that atoms are able to connect and disconnect from one another. So I wanted to sit down, take a minute to discuss the possibilities. But one thing that really struck me recently, I was at one of our family members' houses and they had the book Gödel, Escher, Bach, which you guys have probably read. And I checked it out when I was much younger, and it was very intriguing, and it sort of recounts this idea that theories and explanations and descriptions of nature are inherently incomplete because you're always able to delve deeper and find a new layer of patterns and a new layer of connections. And one thing that really strikes us about the shape of the fiber is that in order for it to latch and unlatch, it must articulate. And what we're talking about is the fiber that actually constructs these structures that connect the atoms and the structure of the surface of the atom, the same fiber. It has to be able to flex in order to take connections and break connections. So what has historically been done in similar situations, say with molecular bonding, is that we treat the entities, the bodies, as if they are catch loop systems. They have some binding energy, and once you overcome that, you pull hard enough, they come apart. Now,
and this is accomplished through hydrogen bonding, London forces, van der Waals forces. These are not ionic bonds the way, or covalent they're not covalent bonds the way that you would find inside of, say, a grain of salt. These are temporary interactions that are highly specific because of this lock and key type of interaction, because they fit so well together. They hold.
And so the way that people have treated these sort of bonding interactions in the past is they ascribe this concept of charge to different pieces of the structure, right? I think a water molecule is a really great example of this. It has a polar character, right? It has a negative region, it has a positive region, and these pairs of opposite attracting regions have schematically allowed people to make progress in those sciences and understand how these molecules can interact, even if they don't totally understand the enmeshment process. And so,
in other words, like when you ask them what is charge, they don't have a clear answer, or they say, well, that's a great question, no one really knows. But just as with the theory of heat, where you have this phlogiston sort of substance that creates heat, it's good enough to work with for a while, until you get to the very edge of understanding and the very edge of science and technology, because that's when you really have to figure out a new conception of the world that lets you delve deeper than where you've been before. And that's where we're at right now with this.
And it's really worth pointing out that all of the work that went into describing atomic interactions in terms of charge was really useful to us and people like us who are working on material explanations, because we're able to take all of that schematization and try to imagine what sort of material actors could be accomplishing that. And so in the case of charge, we've explained that in terms of the atomic shells actually frictionally engaging with one another, right? And we have this particular idea of spin 1/2 with regard to the electron, which describes how the electron rotates in this sort of vortex that's involuting and pulling, and it pulls the atoms together and it holds them together frictionally. And so when we start to think about what sort of similar processes could be involved in holding the fibers together, but transiently, so they're able to allow the filaments to connect and disconnect from atoms and filamentary transit through space, we have to think about some sort of similar process going on. And it starts to make a lot of sense to us, especially when we start thinking about the representations. I mean, when I'm really inspired by the representations of Escher and Bach and this fractal nesting of form, because it seems like when you look at nature, you do see things that are very self-similar at different scales, right? We see these vortex formations of storms on the surfaces of planets that very much mirror the organization of disk galaxies and spiral galaxies. And so we very much expect that the atom's shape itself will reflect such a similar vortex shape. And this isn't a new idea, right? Maxwell had this idea. People who were working before the death of the ether had this same vortex notion. And so
so this is like a fractal vortex notion.
Yeah, it's not exactly a vortex. I mean, check out like our video on spin 1/2 and understand what we mean by an involuting surface of an orbital shell. But I think we're going to have to start to model the fiber as having a polar structure, a polar architecture, which allows it to grab at one end and receive at another end. And that is going to inherently require it to have subfibers, second-degree fibers. And there may be, and honestly, I suspect very much that there's a repeating complexity that emerges the deeper we probe. Once we have the energies to be able to explore the shape of the primary fibers, we're gonna find secondary fibers. We're gonna find tertiary fibers, right? There's no reason for me to believe that we're going to ever have a complete theory of nature. And this also goes back to the Gödel, Escher, Bach. Gödel's incompleteness theorem. There's always going to be new information that emerges and helps us construct a more complete version of our theory, but it's never going to be totally complete. And so we have to be okay with making these approximations like people have done in the past with the concept of charge.
Yeah, I think it's Gödel.
Gödel. Gödel.
Let's call it.
All right, see you guys next time.
See ya.